ʻINIAC was the first electronic general-purpose computer. It was Turing-complete, digital, and capable of being reprogrammed to solve a large class of numerical problems. ʻINIAC was initially designed to calculate artillery firing tables for the United States Army's Ballistic Research Laboratory. When ʻINIAC was announced in 1946, it was heralded in the press as a giant brain. It had a speed of 1,000 times that of electromechanical machines. This computational power, coupled with general-purpose programmability, excited scientists and industrialists. ʻINIAC's design and construction was financed by the United States Army, Ordnance Corps, Research and Development Command, which was led by Major General Gladian Marcus Barnes. He was Chief of Research and Engineering, the Chief of the Research and Development Service, Office of the Chief of Ordnance during World War II. The construction contract was signed on June 5, 1943, and work on the computer began in secret by the University of Pennsylvania's Moore School of Electrical Engineering starting the following month under the codename Project PX. The completed machine was announced to the public the evening of February 14, 1946, and formally dedicated the next day at the University of Pennsylvania, having cost almost $500,000. It was formally accepted by the U.S. Army Ordnance Corps in July 1946. ʻINIAC was shut down on November 9, 1946 for a refurbishment and a memory upgrade, and was transferred to Aberdeen Proving Ground, Maryland in 1947. There, on July 29, 1947, it was turned on and was in continuous operation until 11:45 p.m. on October 2, 1955. Finished shortly after the end of World War II, one of its first programs was a study of the feasibility of the hydrogen bomb. A few months after its unveiling, in the summer of 1946, as part of an extraordinary effort to jumpstart research in the field, the Pentagon invited the top people in electronics and mathematics from the United States and Great Britain to a series of 48 lectures altogether called the Theory and Techniques for Design of Digital Computers, more often named the Moore School Lectures. Half of these lectures were given by the inventors of ʻINIAC. ʻINIAC was conceived and designed by John Mauchly and J. Presperekert of the University of Pennsylvania. The team of design engineers assisting the development included Robert F. Shaw, Jeffrey Chuan-Chu, Thomas Kite Sharpless, Arthur Burks, Harry Huskey and Jack Davis. ʻINIAC was named an IEEE milestone in 1987. Description: ʻINIAC was a modular computer, composed of individual panels to perform different functions. 20 of these modules were accumulators, which could not only add and subtract but hold a 10-digit decimal number in memory. Numbers were passed between these units across several general-purpose buses, or trays, as they were called. In order to achieve its high speed, the panels had to send and receive numbers, compute, save the answer, and trigger the next operation all without any moving parts. Key to its versatility was the ability to branch. It could trigger different operations that depended on the sign of a computed result. ʻINIAC contained 17,468 vacuum tubes, 7,200 crystal diodes, 1,500 relays, 70,000 resistors, 10,000 capacitors and around 5 million hand-soldered joints. It weighed more than 30 short tons, was roughly 8 by 3 by 100 feet, took up 1,800 square feet, and consumed 150 kilowatts of power. This led to the rumor that whenever the computer was switched on, lights in Philadelphia dimmed. Input was possible from an IBM card reader, and an IBM card punch was used for output. These cards could be used to produce printed output offline using an IBM accounting machine, such as the IBM 405. ʻINIAC used 10-position ring counters to store digits. Each digit used 36 vacuum tubes, 10 of which were the dual triodes making up the flip-flops of the ring counter. Arithmetic was performed by counting pulses with the ring counters and generating carry pulses if the counter wrapped around, the idea being to emulate in electronics the operation of the digit wheels of a mechanical adding machine. ʻINIAC had 20 10-digit signed accumulators which used tens complement representation and could perform 5,000 simple addition or subtraction operations between any of them and a source every second. It was possible to connect several accumulators to run simultaneously, so the peak speed of operation was potentially much higher due to parallel operation. It was possible to wire the carry of one accumulator into another accumulator to perform double precision arithmetic, but the accumulator carry's circuit timing prevented the wiring of 3 or more for even higher precision. ʻINIAC used 4 of the accumulators, controlled by a special multiplier unit, to perform up to 385 multiplication operations per second. 5 of the accumulators were controlled by a special divider's square root unit to perform up to 40 division operations per second or 3 square root operations per second. The other 9 units in ʻINIAC were the initiating unit, the cycling unit, the master programmer, the reader, the printer, the constant transmitter, and 3 function tables. The references by Rojas and Hashajian give more details about the times for operations, which differ somewhat from those stated above. The basic machine cycle was 200 microseconds, or 5,000 cycles per second for operations on the 10-digit numbers. In one of these cycles, ʻINIAC could write a number to a register, read a number from a register, or add/subtract 2 numbers. A multiplication of a 10-digit number by a d-digit number took d plus 4 cycles, so a 10 by 10-digit multiplication took 14 cycles, or 2800 microseconds a rate of 357 per second. If one of the numbers had fewer than 10 digits, the operation was faster. Division and square roots took 13, d plus 1, cycles, where d is the number of digits in the result. So a division or square root took up to 143 cycles, or 28,600 microseconds a rate of 35 per second. If the result had fewer than 10 digits, it was obtained faster. Reliability: ʻINIAC used common octal base radio tubes of the day. The decimal accumulators were made of 6SN7 flip-flops, while 6L7s, 6SJ7s, 6SA7s and 6AC7s were used in logic functions. Numerous 6L6s and 6V6s served as line drivers to drive pulses through cables between rack assemblies. Several tubes burned out almost every day, leaving it non-functional about half the time. Special high-reliability tubes were not available until 1948. Most of these failures, however, occurred during the warm-up and cool-down periods, when the tube heaters and cathodes were under the most thermal stress. Engineers reduced ʻINIAC's tube failures to the more acceptable rate of 1 tube every 2 days. According to a 1989 interview with Eckert, "We had a tube fail about every 2 days and we could locate the problem within 15 minutes. In 1954, the longest continuous period of operation without a failure was 116 hours close to 5 days. Programming: although the Ballistic Research Laboratory was the sponsor of ʻINIAC, 1 year into this 3-year project John von Neumann, a mathematician working on the hydrogen bomb at Los Alamos, became aware of this computer. Los Alamos subsequently became so involved with ʻINIAC that the first test problem ran consisted of computations for the hydrogen bomb, not artillery tables. The input-output for this test was 1 million cards. ʻINIAC could be programmed to perform complex sequences of operations, including loops, branches, and subroutines. The task of taking a problem and mapping it onto the machine was complex, and usually took weeks. After the program was figured out on paper, the process of getting the program into ʻINIAC by manipulating its switches and cables could take days. This was followed by a period of verification and debugging, aided by the ability to execute the program step by step. In 1997, the 6 women who did most of the programming of ʻINIAC were inducted into the Women in Technology International Hall of Fame. As they were called by each other in 1946, they were Kay McNulty, Betty Jennings, Betty Snyder, Marlin Westcoff, Fran Billers and Ruth Lichterman. Jennifer S. Light's essay, "When Computers Were Women," documents and describes the role of the women of ʻINIAC as well as outlines the historical omission or downplay of women's roles in computer science history. The role of the ʻINIAC programmers was also treated in a 2010 documentary film titled Top Secret Roses, The Female Computers of WWII by Ann Erickson. ʻINIAC was a one-of-a-kind design and was never repeated. The freeze on design in 1943 meant that the computer design would lack some innovations that soon became well-developed, notably the ability to store a program. Eckert and Mauchly started work on a new design, to be later called the ʻEDVAC, which would be both simpler and more powerful. In particular, in 1944 Eckert wrote his description of a memory unit which would hold both the data and the program. John von Neumann, who was consulting for the Morse School on the ʻEDVAC, sat in on the Morse School meetings at which the stored program concept was elaborated. Von Neumann wrote up an incomplete set of notes which were intended to be used as an internal memorandum describing, elaborating, and couching in formal logical language the ideas developed in the meetings. ʻENIAC Administrator and Security Officer Herman Goldstein distributed copies of this first draft to a number of government and educational institutions, spurring widespread interest in the construction of a new generation of electronic computing machines, including EDSAC at Cambridge, England and SEAC at the U.S. Bureau of Standards. A number of improvements were also made to ʻENIAC after 1948, including a primitive read-only stored programming mechanism using the function tables as program ROM, an idea included in the ʻENIAC patent and proposed independently by Dr. Richard Klippinger of BRL. Klippinger consulted with von Neumann on what instruction set to implement. Klippinger had thought of a three-address architecture while von Neumann proposed a one-address architecture because it was simpler to implement. 3 digits of one accumulator were used as the program counter, another accumulator was used as the main accumulator, a third accumulator was used as the address pointer for reading data from the function tables, and most of the other accumulators were used for data memory. The programming of the stored program for ʻENIAC was done by Betty Jennings, Klippinger and Adele Goldstein. It was first demonstrated as a stored program computer on September 16, 1948, running a program by Adele Goldstein for John von Neumann. This modification reduced the speed of ʻENIAC by a factor of 6 and eliminated the ability of parallel computation, but as it also reduced the reprogramming time to hours instead of days, it was considered well worth the loss of performance. Also, analysis had shown that due to differences between the electronic speed of computation and the electromechanical speed of input-output, almost any real-world problem was completely I/O bound, even without making use of the original machine's parallelism. Most computations would still be I/O bound, even after the speed reduction imposed by this modification. Early in 1952, a high-speed shifter was added, which improved the speed for shifting by a factor of 5. In July 1953, a 100-word expansion core memory was added to the system, using binary-coded decimal, XS3 number representation. To support this expansion memory, ʻENIAC was equipped with a new function table selector, a memory address selector, pulse shaping circuits, and 3 new orders were added to the programming mechanism. Comparison with other early computers. Mechanical and electrical computing machines have been around since the 19th century, but the 1930s and 1940s are considered the beginning of the modern computer era. The Bell Telephone Labs complex number calculator, a relay-based computer developed by George R. Stibitz in 1939, 40 at Bell's New York City laboratory and demonstrated remotely from Hanover, New Hampshire at the 1940 Mathematics Conference at Dartmouth College. The German Z3 was designed by Konrad Zuse. It was the first programmable computer, but it was electromechanical, rather than electronic, as it used relays for all functions. It computed logically using binary arithmetic. It was programmable by punch tape, but lacked the conditional branch. While not designed for Turing completeness, it accidentally was, as it was found out in 1998. It was destroyed in a bombing raid on Berlin in December 1943. The American Atanasoff Berry computer was the first completely electronic computing device. It implemented binary computation with vacuum tubes but was not general purpose, being limited to solving systems of linear equations. It also did not exploit electronic computing speeds, being limited by a rotating capacitor drum memory and an input-output system that was intended to write intermediate results to paper cards. It was manually controlled and was not programmable. The 10 British Colossus computers were designed by Tommy Flowers. The Colossus computers were digital, electronic, and were programmed by plugboard and switches, but they were dedicated to code breaking and not general purpose. Howard Aiken's 1944 Harvard Mark I was programmed by punched tape and used relays. It performed general arithmetic functions, but lacked any branching. ʻINIAC was, like the Z3 and Mark I, able to run an arbitrary sequence of mathematical operations, but did not read them from a tape. Like the Colossus, it was programmed by plugboard and switches. ʻINIAC combined full, Turing-complete programmability with electronic speed. The ABC, ʻINIAC and Colossus all used thermionic valves. ʻINIAC's registers performed decimal arithmetic, rather than binary arithmetic like the Z3 or the Atanasoff Berry computer. The Manchester Small-Scale Experimental Machine, nicknamed Baby, was the world's first stored program computer. It was built at the Victoria University of Manchester by Frederick C. Williams, Tom Kilburn and Jeff Tootle, and ran its first program on June 21, 1948. The machine was not intended to be a practical computer but was instead designed as a testbed for the Williams tube, an early form of computer memory. Although considered small and primitive by the standards of its time, it was the first working machine to contain all of the elements essential to a modern electronic computer. As soon as the SSEM had demonstrated the feasibility of his design, a project was initiated at the university to develop it into a more usable computer, the Manchester Mark I. The Mark I in turn quickly became the prototype for the Ferranti Mark I, the world's first commercially available general-purpose computer. The SSEM had a 32-bit word length and a memory of 32 words. As it was designed to be the simplest possible stored program computer, the only arithmetic operations implemented in hardware were subtraction and negation. Other arithmetic operations were implemented in software. The first of 3 programs written for the machine found the highest proper divisor of 218, a calculation that was known would take a long time to rule a euro, and so prove the computer's reliability a euro by testing every integer from 218 or 1 downwards, as division was implemented by repeated subtraction of the divisor. The program consisted of 17 instructions and ran for 52 minutes before reaching the correct answer of 131,072, after the SSEM had performed 3.5 million operations. Shortly after, Alan Turing wrote the third program to be executed on the machine, which was to perform long division. The SSEM did not require rewiring to reprogram as it supported stored programs, and as such can be argued to be the world's first modern digital computer. Until 1948, ʻINIAC required rewiring to reprogram, like the Colossus. The idea of the stored program computer with combined memory for program and data was conceived during the development of ʻINIAC, but it was not initially implemented in ʻINIAC because World War II priorities required the machine to be completed quickly, and ʻINIAC's 20 storage locations would be too small to hold data and programs. Public knowledge, the Z3 and Colossus were developed independently of each other and of the ABC and ʻINIAC during World War II. The Z3 was destroyed by Allied bombing of Berlin in 1943. The Colossus machines were part of the UK's war effort. Their existence only became generally known in the 1970s, though knowledge of their capabilities remained among their UK staff and invited Americans. All but 2 of the machines that remained in use in GCHQ until the 1960s, were destroyed in 1945. The ABC was dismantled by Iowa State University, after John Atanasoff was called to Washington, D.C., to do physics research for the U.S. Navy. ʻINIAC, by contrast, was put through its paces for the press in 1946, and captured the world's imagination. Older histories of computing may therefore not be comprehensive in their coverage and analysis of this period. Patent. For a variety of reasons, U.S. Patent 3,120,606 for ʻINIAC, granted in 1964, was voided by the 1973 decision of the landmark federal court case Honeywell v. Sperry Rand, putting the invention of the electronic digital computer in the public domain and providing legal recognition to Atanasoff as the inventor of the first electronic digital computer. Parts on display. The School of Engineering and Applied Science at the University of Pennsylvania has 4 of the original 40 panels and 1 of the 3 function tables of ʻINIAC. The Smithsonian has 5 panels in the National Museum of American History in Washington, D.C. The Science Museum in London has a receiver unit on display. The Computer History Museum in Mountain View, California has 3 panels and a function table on display. The University of Michigan in Ann Arbor has 4 panels, salvaged by Arthur Burks. The U.S. Army Ordnance Museum at Aberdeen Proving Ground, Maryland, where ʻINIAC was used, has one of the function tables. The Barreau Group in Plano, Texas has also 7 panels and detailed history and explanation of ʻINIAC functions using text, graphics, photographs and interactive touchscreen. The U.S. Military Academy at West Point, New York has one of the data entry terminals from the ʻINIAC. In 1995, a very small silicon chip measuring 7.44 mm by 5.29 mm was built with the same functionality as ʻINIAC. Although this 20 MHz chip was many times faster than ʻINIAC, it was still many times slower than modern microprocessors of the late 90s. See also, History of Computing, History of Computing Hardware, List of vacuum tube computers, military computers. Notes. References. Further reading. External links, ʻINIAC simulation, another ʻINIAC simulation, ʻINIAC on a chip, ʻINIAC from Computing Dictionary, Q&A, a lost interview with ʻINIAC co-inventor J. Presper Eckert, interview with Eckert, transcript of a video interview with Eckert by David Allison for the National Museum of American History, Smithsonian Institution on February 2, 1988. An in-depth, technical discussion on ʻINIAC, including the thought process behind the design. Oral history interview with J. Presper Eckert, Charles Babbage Institute, University of Minnesota. Eckert, a co-inventor of ʻINIAC, discusses its development at the University of Pennsylvania's Moore School of Electrical Engineering. Describes difficulties in securing patent rights for ʻINIAC and the problems posed by the circulation of John von Neumann's 1945 first draft of the report on ʻEDVAC, which placed the ʻINIAC inventions in the public domain. Interview by Nancy Stern, October 28, 1977. Oral history interview with Carl Chambers, Charles Babbage Institute, University of Minnesota. Chambers discusses the initiation and progress of the ʻINIAC project at the University of Pennsylvania Moore School of Electrical Engineering. Oral history interview by Nancy B. Stern, November 30, 1977. Oral history interview with Irvin A. Travis, Charles Babbage Institute, University of Minnesota. Travis describes the ʻINIAC project at the University of Pennsylvania, the technical and leadership abilities of Chief Engineer Eckert, the working relations between John Mauchly and Eckert, the disputes over patent rights, and their resignation from the university. Oral history interview by Nancy B. Stern, October 21, 1977. Oral history interview with S. Reed Warren, Charles Babbage Institute, University of Minnesota. Warren served as supervisor of the ʻEDVAC project. Central to his discussion are J. Presper Eckert and John Mauchly and their disagreements with administrators over patent rights. Discusses John von Neumann's 1945 draft report on the ʻEDVAC, and its lack of proper acknowledgement of all the ʻEDVAC contributors. ʻINIAC Programmers Project, The Women of ʻINIAC, Programming ʻINIAC, Programming Example for the Modulo Function, How ʻINIAC Took a Square Root, Mike Mayuse, Collected ʻINIAC Documents, ʻIniac chapter in Karl Kempf, Electronic Computers Within the Ordnance Corps, November 1961, The ʻIniac Story, Martin H. Wake, Ordnance Ballistic Research Laboratories, 1961, ʻIniac Museum at the University of Pennsylvania, ʻIniac Specifications from Ballistic Research Laboratories Report No. 971 December 1955, U.S. Patent 3,120,606 issued in 1964 for ʻIniac, also PDF version, A Computer is Born, Michael Canillos, 60th Anniversary News Story, Connect, February 13, 2006, Gumbrecht, Jamie. Rediscovering WWIized Computers. CNN.com. Retrieved February 9, 2011 A.